All right, what's up, everybody? Welcome back. We're going to be talking more about ionic compounds in water. Namely, we're going to talk about two different energies associated with ionic compounds. And, they're really important energies to consider when you're talking about ionic solubility in water. And these two energies are lattice energy and hydration energy. So, first off, let us consider lattice energy. And even before we consider lattice energy, let's talk about a lattice. What is a lattice exactly? And you can probably find a more clear and concise definition of what a lattice is somewhere online, maybe Wikipedia. But a lot of these definitions of lattice, or really any scientific term you find online or in a lot of textbooks, oftentimes these terms are kind of complicated in their explanation. So I'm going to try to make this as simple as possible. So anyway, a lattice. What is a lattice? In order to conceptualize what a lattice is, let's take a look at this little drawing I have here. So we have sodium chloride, and notice we have alternating sodium, chloride, sodium, right? So we have a sodium ion, and then a chloride ion, then a sodium ion, then a chloride ion, and this goes on and on. And now, my whiteboard here, it's essentially a two-dimensional plane, but imagine this in three dimensions, right? So you have this three-dimensional structure, and within this three-dimensional structure, you have alternating sodium and then chloride and then sodium and then chloride, and this goes on in three different dimensions, right? That's basically a lattice. You have this three-dimensional structure of alternating sodium chloride ions. That's essentially your lattice, your crystal lattice. Now, what is lattice energy? Again, you could probably find maybe a more clear and concise definition online, although oftentimes when I look at these definitions, they're ridiculous. They use all these big, crazy words in their definition, and it makes it even harder to understand what they're trying to explain. So basically, lattice energy is this. Say you had a sodium ion over here, chloride ion over here, sodium ion over here, chloride ion over here. You have all these ions, and they're all separated from one another. Now, let's say you were going to take all of these ions and sort of push them together, right? You're going to force them together so that they form a lattice. The energy required to bring all of those ions together and to force them to make a lattice, that's going to be your lattice energy. Essentially, again, you can look up definitions online, but for a basic understanding of what lattice energy is, it's just the energy required to bring all of these ions together and force them into a lattice structure, right? So that's lattice energy. That's the first energy I wanted to talk about in this video. The second, again, is hydration energy. So if you saw part one of this video, we basically took some sodium chloride, some solid sodium chloride, and we put it into water. And that solid sodium chloride, there was sodium, there was chloride, those ions separated, right? They dissociated from one another. And that dissociation is at least partially driven by hydration. And basically, when something's getting hydrated, it's getting surrounded by water molecules. So when those ions separated from one another, part of that separation at least occurred because the ions were forming favorable interactions with that water. So for example, say we had a sodium ion here, right? Now that sodium ion is going to become hydrated, meaning water is just going to surround this sodium ion, right? The sodium ion becomes hydrated. It's forming favorable interactions with the water molecules surrounding it. Similar thing happens to the chloride ions, right? When chloride gets hydrated, it's basically getting surrounded by a bunch of water molecules. So that's basically hydration. It's just when you have some structure or some chemical entity, in this case ions, and these ions are getting surrounded by a bunch of water molecules. That's basically hydration. And so hydration energy is essentially the energy that's released when these favorable interactions form. So you have a water molecule here, right? And it's going to interact with this sodium ion. And when that interaction occurs, there's going to be a release of energy, and that's the hydration energy. It's just the energy that is released when some chemical agent, some chemical species is hydrated. It's the energy released when this chemical, when this ion here is surrounded by water. That's your hydration energy. So let's talk about hydration though. Why does that happen? You know, that seems sort of weird. Why are all of these water molecules just going to surround these ions? It seems kind of weird. And if you look at these two pictures, there's something else here that's kind of weird. Let's take a look, for example, over here first. Notice that in this picture, we have our sodium ion in the middle, and we have these waters surrounding this sodium ion. Now notice that in all of these water molecules, whichever one you look at doesn't matter, notice that these water molecules, the oxygens are pointing towards the sodium, right? But over here, the hydrogens point towards the chloride. And that's basically going to be the basis of hydration and why hydration occurs. This probably doesn't make much sense right now, but in order to make sense of it, why don't we consider really quickly, water molecule itself, the structure of the water molecule. So, assuming you've learned how to do some work with Lewis structures, and maybe you've been exposed to Vesper theory before, you know that water is actually a bent molecule, right? So using your imagination here, let me get a different color. Using your imagination here, you'll have an oxygen, a hydrogen, and then we'll have our lone pairs up here. And so, again, if you've seen some Lewis structures before, you know how to draw them. Maybe you've been exposed to Vesper theory. You know that water is actually a bent molecule with regards to its geometry. Now, not only is water bent, it's also polar. Polar just refers to the fact that this molecule has atoms of different elements in here, and those different elements have different electronegativities. So you can basically think of electronegativity as the tendency of an atom within a molecule or a polyatomic ion to pull electron density towards itself. Now, the most electronegative element on the periodic table is fluorine. And as you approach fluorine on the periodic table, elements tend to become pretty electronegative. So, you know, oxygen, nitrogen, chlorine, bromine, all of these are pretty electronegative elements. They also tend to be pretty close nearby fluorine on the periodic table. To contrast that, you have elements like cesium and sodium, lithium, hydrogen. These elements are all pretty far away from fluorine, and so they're not very electronegative. They're actually pretty electropositive. All right, and to sort of denote that certain atoms, certain elements are electronegative and electropositive, we use this Greek delta. So, for example, oxygen. Oxygen is pretty electronegative, right? It has a tendency to pull electron density towards itself when it's within molecules. So we use this symbol here, the Greek delta with a negative sign. And that just shows that this oxygen is partially negative. Now these hydrogens down here, they're partially positive, right? They don't really pull electron density towards themselves in the same way that oxygen would, for example. So we said that because of Vesper theory, water is going to be a bent molecule. And we also said because hydrogen and oxygen, because these two elements have different electronegativities, the water molecule itself is actually going to be polar, right? With a partial positive charge fixated primarily over the hydrogens, partial negative charge associated with this oxygen here. Now, these partial positive and negative charges definitely, well, partially at least, explain what's going on here. So for example, the sodium ion, positively charged, right? And in chemistry and physics, and well, really it's science in general, negative charges like to interact with positive charges. Positive charges like interacting with negative charges. Opposites attract, right? And so that's exactly what's going on here. The positive charge associated with this sodium, that positive charge is going to want to interact with that partial negative charge associated with the oxygen. And as such, oxygen is going to point itself towards that sodium, right? So you have all these partially negative oxygens, and they're going to want to interact with this positively charged sodium, and that interaction is going to result in a release of energy. Similar things going on over here, you know. All of the hydrogens are oriented such that they're pointing towards the chloride, and that makes sense, right? Because chloride's a negatively charged ion, right? Chloride's negatively charged. And within the water molecule, we already said that hydrogens tend to be partially positive. And so, let me grab this marker here. Those partial positive charges on those hydrogens here, they can actually interact with that negative charge on the chloride, right? And because you have these opposite charges interacting with one another, you're going to get a release of energy. Well, we've talked about a few things, right? We talked about lattice energy, hydration energy, but what does this really have to do with figuring out whether or not an ionic compound will dissolve in water? And that's a great question. Let's just really quickly, again, remind ourselves what lattice energy is. Lattice energy is essentially the energy required to bring all of these ions together, right? You have all these ions that are far apart from one another. You're going to force them together into this lattice, and that takes energy. So lattice energy typically has a positive sign associated with it. Hydration energy typically has a negative sign associated with it, right? Because it's the energy that's released when an ion interacts with water. And so in order to figure out whether or not some ionic compound will dissolve in water, you can actually compare these two different energies, right? So if the magnitude, for example, just look at the magnitudes of these respective energies. If the magnitude of the hydration energy is greater than the magnitude of the lattice energy, that ionic compound will likely be soluble in water, right? The contrary is also true. If you look at the magnitudes of these respective energies here, and if the magnitude of the lattice energy is greater than the magnitude of the hydration energy, that ionic compound, it's probably not really going to dissolve, man. It's probably just going to stay as a lattice in solution, you know. It's going to be pretty darn insoluble in water. All right? So if lattice energy is greater in magnitude, ionic compound's probably not really soluble. If hydration energy is greater in magnitude than the lattice energy, the ionic compound probably will dissolve. Now, here's a question I have for everyone watching this. These two energies are opposite in sign, right? Lattice energy tends to be positive. Hydration energy tends to have a negative sign associated with it. So with these opposite signs, just consider the magnitude again. What would happen if the magnitude of these two respective energies were the same? What would you expect? Would you expect the ionic compound to be soluble, partially soluble, probably not soluble at all? Let me know what you think in the comments below. And of course, if you had any questions about either one of these energies or anything we talked about in this video, whether it's, you know, lattice energy, hydration energy, water, the polarity of water, Vesper theory, Lewis structures, whatever. You know, if you have any questions about any of this or anything else, let me know in the comments below. And thanks for watching. Take care and stay tuned.